Okay, so once again, good morning, everyone. So for today, we're going to have a discussions about system modeling, of course, module number 5 for the advanced software engineering. Uh, okay, so in this lesson, we look forward that we will be able to introduce some types of system model that may be developed as part of the requirements engineering and a system design processes. No, we will look forward that we will be able to understand how graphical models can be used to represent software systems, understand why different types of model are required, and the fundamental system modeling perspective of context, interaction structure, and behavior. And we will be able to have been introduced to some of the diagram types, specifically when it comes to unified modeling language and how these diagrams may be used in the system modeling. And lastly, be aware of the ideas underlying model-driven engineering, where a system is automatically generated from structural and behavioral model. So again, system modeling is the process of developing abstract model of a system. Uh, Before, no, during our time, no, especially in our software engineering, introduction to software engineering in a collegiate level, no, we look forward just for the uh, flow chart, data flow diagram. But right now, we look forward for the system architecture and some system modeling, because system modeling has generally come to mean representing the system using some kind of graphical notation, which is now almost always been on notations in the unified modeling language. However, it is also possible to develop formal, specifically mathematical, no, model of a system, usually as a detailed system specification. Okay, so models are used during the requirements engineering process to help derive the requirements for the system. And during the design process to describe the system to engineering implementations, the system and after implementation to the document, the system's structure and operation. And you may develop actually models of both the existing system and the system to be developed, because models of the existing system are used during requirement engineering, right? And they help clarify what the existing system does and can be used as a basis for discussing strengths and weaknesses. And this then lead to requirements, no, for the new system. Another thing is that models of the new system are used during requirements engineering to help explain the proposed requirements to other system stakeholders, because most commonly we need to consider the stakeholders, specifically the user. No, engineers use these models to discuss design protocols and to document the system for implementation. In a model-driven engineering process, it is possible to generate a complete or either partial system implementations from the system model. We need to understand that the most important aspect of a system model is that it leaves out detail. No? A model is an abstraction of the system being studied rather than an alternative presentation of that system. Ideally, a presentation of a system should maintain all the information about the entity being presented. An abstract deliberately simplifies the picks out that most salient characteristics. An abstraction, of course, let's say, for example, no, in the very unlikely event of this discussion being serialized in a textbook, the presentation there would be an abstraction of the book's key points. No, if there were translated from English into, let's say, Chinese, this would be an alternative representation. And the translator intention would be to maintain all the information as it is presented in English. And you may develop different models to represent the system from different perspectives. Now, example, now let's say, for example, an external perspective where your model uh, the context or environment of the system, or an interaction, no, perspective where you're with your model, the interaction between a system and its environment or between the components of a system, or a structural perspective where your model, the organization of a system, or the structure of the data that is processed by the system. But when it comes to a behavioral perspectives, so where your model the dynamic behavior of the system and how it responds to events. These perspectives now, this perspective have much in common with Cruikshan's 4+1 view of system architecture, no, where he suggests, no, that you should document a system architecture and organization from different perspective, no. So I think you're familiar with the activity diagrams. No? Right now, instead of using data flow diagram, we use activity diagrams. No? And there's certain instances that some professors still required us to create or crafted, what do you call this one? Gantt chart. No? But right now, we utilize activity diagram, which shows the activities involved in a process or in a data processing. Others, of course, crafted or created use case diagrams, which shows the interaction between a system and its environment. We have, of course, what we call sequence diagrams, which shows interaction between actors and the system and between system components. The class diagrams naman, which show the object classes in the system and the association between these classes. State diagram will be the last, which show how the system reacts on internal and external events. Okay. Another, of course, is that the unified modeling language is a set of 13 different diagram types that may be used to model software system. It emerged from work in 90s, no, an object-oriented modeling where similar object-oriented notations were integrated to the create of UML. A major revision actually happened, no, was and finalized during 2004. So the UML is a universally accepted as the standard approach for developing models of software system. Variants have been proposed for more general system modeling. At an early stage in the specification of the system, you should decide on the system boundaries. No? This involves working with system stakeholders to decide what functionality should be included in the system and what is provided by the system environment. That is how, actually in layman terms, that is what we call delimitation. No? But technically, when it comes to IT, that is what we call context model. No? Again, as what I have mentioned during our last subject, that delimitation is different from the limitations. Okay? So limitation is uncontrollable. When you say delimitation, we just limit, no, the content, no, or the modules that we could able to develop from this specific software. So you may decide that automated support for some business process should be implemented, but others should be manual process or supported by different systems. So you should look at possible overlaps, no, in functionality with existing system and decide where new functionality should be implemented. And this decision should be made early in the process to limit the system cost and the time needed for understanding the system requirements and design. It is not necessary for us to add on some modules which is not usable for the stakeholders. No, because we need to consider the system cost, right? In some cases, no, the boundary between a system and its environment is relatively clear. Let's say, for example, where an automated system is replacing an existing manual or computerized system, the environment of the new system is usually the same as the existing system's environment. In other cases, no, there is more flexibility, and you decide what constitutes the boundary between the system and environments during the requirement engineering process. So let's say, for example, no, say you are developing the specification for the patient information system for a mental health care. And this system is intended to manage information about patients attending mental health clinics and the treatments, no, that have been prescribed. In developing the specification for this system, you have to decide whether the system should focus exclusively on collecting information about consultation, no, or whether it should also collect personal patient information. The advantage of relying on other system for patient information is that you avoid duplicating data. So the major disadvantages, however, is that using other system may make it slower to access information. If these systems are available, then we could be able to use or cannot be used. Actually, we have the context of different application when it comes to medical health records, specifically the patient record system, management reporting system, admission system, prescription, appointment system, and the HC statistics system. The definition of a system boundary is not a value-free judgment. Social and organizational concern may mean that the position of a system boundary may be determined by non-technical factors. Let's say, for example, a system boundary may be deliberately positioned so that the analysis process can also be carried out on one side. It may be chosen so that a particular difficult manager need not to be consulted. It may be positioned so that the system cost is increased and the system development division must therefore expand to design and implement the system. So when some decisions on the boundaries of the system have been made, part of the analysis activity is the definition of the context and dependency that the system has on its environment. Actually, normally, producing a simple architectural model is the first step in this activity. I just want to share a video presentation for you to have an additional inputs when it comes to system modeling.
About modeling, different aspects and different types of modeling. So system modeling is, as it says, the process of developing abstract models of a system so that you can have different views on the system. We're going to be using UML, the Unified Modeling Language, to do this. And the aim is to understand more deeply what the connections between the different parts of the system being designed are, right? Because we need to understand that because we may find things about the design, but the main reason we're doing it up front is to find more things about the requirements. As it says, they help clarify what the existing system does, which may help find strengths and weaknesses, and it's to help explain to the stakeholders the requirements. Model-driven engineering across all sorts of engineering is very useful because it's more of a paper study, and paper studies can be done much more quickly and much more cost effectively before we decide to actually build whatever it is we're trying to build. So system modeling is very important. Right? So there's various perspectives of the system. There's the external perspective. There's an interaction perspective, how the system works between itself and the environment. There's a structural perspective. What's the organization of the system? And then there's a behavioral perspective, which is how does the system change over time? What's its behavior over time? The sorts of diagrams we're going to use are activity diagrams, use case diagrams, sequence diagrams, class diagrams, and state diagrams. We've already done quite a bit on use case diagrams, and we've started to look at sequence and class diagrams. We still need to cover in class what activity and state diagrams are doing. And the aim with these is you can use UML to be very pedantic and very specific, but for me the biggest benefit of UML is to be able to draw something for somebody else to discuss software rather than having to code something up to discuss software. And that's the biggest benefit. You can use a case tool, the computer-aided software engineering tool, to be able to build software from UML, but a lot of places don't do that, and it's arguable what the benefit is, depending on the context of the software. It's a useful way of documenting the system. A lot of tools, I believe Eclipse and I believe Visual Studio, allows a level of auto-generation of UML diagrams from the code, which is a nice way of being able to overview the code and see the connections between the code without having to read through lots of code. So context models, they're used to illustrate what the system is doing in context, where it's going to be used. You can deal with social or organisational concerns, and architectural models show how the system sits within potentially complicated IT infrastructure. These days, the IT infrastructure you're likely to meet is a cloud-based system for some parts, a mobile application, a mobile-based system for other parts, and potentially the IT infrastructure between those two. That's why it's very important to determine the system boundary, right? And to some extent, as it says in the third bullet point here, defining the system boundary is a political judgment. You may have to work with people in order to define which parts of the system you're designing you have control over. It may be you don't have control over some parts of the system, even though you're going to be interacting with it. And here's a look at the systems involved in the MentCare case study. There's external systems to MentCare. There's the patient record system, the admission system, the prescription system, appointments, HC statistics, and management reporting, all of which are systems that the thing we're building, in this case MentCare, are going to use or access. So context models only show the environment. They don't show how it's used. So you need process models, and in particular UML activity diagrams, in order to show that. And here's another example. An activity diagram is another name for a flowchart. You've all probably thought about flowcharts. Activity diagram is just a bit more of a what's the word, specified, or a bit more pedantic look at a flowchart. So the flowchart starts with the fixed blue dot in the top left, and it ends with the white annulus blue dot on the right hand side. Okay, so there's lots of various steps. You can see there are guard conditions, right? Not available, available, dangerous, not dangerous. There are parallel paths through the system, right? You can do these things at the same time. You can do these three things at the same time. There's only one path from here to here, but there's three possible ways, but it only happens in one of those three possible ways. Interaction models, right? You want to know how the user's going to use the system. You want to know how systems talk to each other. You want to know how components within a system talk to each other. And use case diagrams and sequence diagrams are the way we do that. We've already talked about use cases, so I'm not going to delve too much into that. You need to have usually the use case diagram as well as the use case report. Right, there's a use case diagram. In this case, the use case association between medical receptionist and transferred data is directed, and that's because well, I'm not quite sure why it's because I would expect in most associations you need two-way communication, as I think I've commented before. Here's an example of the Somerville template for a use case. It's a little different from the one we've been using, but not especially. It's got similar fields. You should have mostly the same information as the template we've been using. Right, and here's a more complex one that just involves the medical receptionist and the functions that they need to perform. The thing that use case diagrams don't do is that they don't show step by step how things happen. The use case reports will do that. The basic or the happy flow will do that, but the UML diagram that shows that is the sequence diagram. And here's a sequence diagram. We've got the medical receptionist on the left hand side, and I think I mentioned that these black dotted lines are the timeline. Time is increasing as we go down the diagram. These blue lines, these thick blue boxes, they're called lifetimes. Right? So the medical receptionist exists for the whole of this sequence diagram, but the authorization only needs to exist for a short period in order to get the authorization to access the system. And then here we've got a guard condition. Only one of these things happens. If the authorization is okay, we get the patient info. If the authorization fails for whatever reason, then we get an error. And here's another one with another system which looks like it's helping us log in, similar to the way that when you log in to most things for Fairfield University, you get directed to the single sign-on page before being redirected to whichever aspect of the IT system within Fairfield that you're using. Sequence diagrams, as I said, talk about interactions and time-based things. Use case diagrams don't. The other thing that we need to start doing with our thinking about software is structural models, right? It starts to set the organization of the components of the system. They can be static or they can be dynamic, depending on the context of what the model is trying to achieve. We've already looked a little bit at class diagrams, and this is now starting to sound like software, right? Class diagrams show the name of the class, potentially the stereotype of the class, the information or the data contained in the class, the fields of the class, their types, their protection levels, and also the methods and their protection levels on the class. Right, and here's where you might start. You don't know too much about it yet. We know we have a patient class and we have a patient record class. And here's a lot of others. And remember, I talked about the numbers, 1 ... star or 1 or whatever on each of these associations, that's talking about the multiplicity of the class nearest the range, right? So down the bottom here, for some reason, they've decided that a consultation is only run by up to 4 doctors. You can't have an unknown number of doctors involved in a consultation. And here's an example of how you might write the consultation class. Consultation class has doctors, date, time, clinic, reason, medication prescribed, treatment prescribed, voice notes, etc. And then the methods are new, prescribe, record notes, transcribe, etc. A very important relationship when we talk about object-oriented programming or object-oriented analysis and design is generalization or inheritance, right? So rather than go into excruciating detail in lots of different things, some parts of those lots of different things are in common. So we try and generalize from all of the entity classes that we've got into something, a subset of their fields and methods that are generalizable. Right? And I'm not going to read through this. You can read through the slides as well as I can. But the idea here is that we use this sort of arrow, this open arrow, or rather unfilled in arrow, where we have the general class is the doctor, but we can be more specific in that the general practitioner is a type of doctor. The hospital doctor is a type of doctor. The consultant is a type of hospital doctor who's a type of doctor. The team doctor is a type of hospital doctor. The trainee doctor is a team doctor, is a hospital doctor, is a doctor. The qualified doctor is a type of team doctor, which is a type of hospital doctor, which is a type of doctor. Okay, that's inheritance. And usually what you do with inheritance is you add some extra information, right? In the case of a hospital doctor, you might they are internal and you might have a staff number and a pager number. For a general practitioner or a primary care physician, they may not be internal to our hospital or our health facility, so you need to know the name of their practice and the address of their practice. So this is an aggregation model, and the idea is that it shows how the different classes are connected to each other. And in this case, aggregation is using the open diamond for the connections, and you can see the multiplicities are also labeled. So behavioral models. These are showing what the dynamic behavior of the system. And there's 2 things that you need to think about that impact the dynamic behavior of your system. There's the data and the events. So a lot of systems are data driven. You get some data in, you process it, you update other data. So understanding what the inputs and outputs and processing are happening is very, very relevant. Right? So here's an example from the insulin pump case study showing how things move from the blood sugar sensor to getting the sensor value, to getting the data, to computing the blood sugar level, to figuring out how much insulin you need, to telling the pump how to deliver that insulin, and then finally delivering the insulin. And here's another sequence diagram example, which shows how we do order processing. And so that first one was about data driven, and now we're more event driven. Mobile applications are often more event driven because you've got people tapping on the screen, you've got notifications arriving. Those things are events, and they're got to be acted on. So state machines are often useful for that. And here's a state diagram, and the top of each of these shapes is the name of the state, right? And we start here, and we can only transition to another state along the arrows. And this is saying we go to full power, we want to set the timer, we set the numbers, the door closes, we can start, the door opens, we disable it, we start again. Once the oven is finished operating or gets cancelled, we wait and then we finish. And again, we're starting at this filled in blue circle and we're finishing at this blue circle with a white annulus around it. You can do things you can nest state diagrams. This is a state chart. You can nest state charts so that one big state, the operation, may have lots of things happening inside it. And these are substates of the operation state. Right, and this is usually you go with a diagram and then a description of each state and a description of each of the transitions for each state. Things that you need. And the one nice thing about model-driven engineering is that it raises the level of abstraction with which you think about the problem and with which you think about solving the problem, and that's very useful. Right? Some of the cons, sometimes the models that you use for abstraction are not great for implementation. And sometimes the savings from generating code may be outweighed by the costs of developing translators for new platforms. So it depends on the system. This is the computer-aided software engineering tools that I'm thinking about. And you can develop a model at different levels, right? There's a computation independent model, there's a platform independent model, and there's platform specific models. And here's a way you may have to move from your original system, your computation independent model, with some domain specific guidelines to get a platform independent model. add to the platform independent model, you add some specific patterns and rules for a platform, which gets you the platform specific model, and then you add some, once you've chosen the language, you add language specific patterns to get executable code. Right, and here's an example of the sort of thing you may want to do. You may start off with a platform independent model that's got to be written in, eventually run in both Java and C#. So this is the way you might achieve that. I'm not convinced by what's happening on this slide. I do think there is a tension between agile and documentation, or agile and architecture, but I don't think that necessarily means that you can you abandon using a level of model-driven architecture. It does help to have a good tool. The tools I've used for model-driven architecture are Rational Rose and Rhapsody. Rational Rose I used for a C++ project or series of projects, and Rhapsody I used for an embedded C project. And C++, but it was an embedded project. One of the things with, if you're developing a system that's got a long lifetime, you may want to think about who's supporting the model-driven architecture software, the tools that you're using. So you may want to work with with a product from a larger company. I believe Rational Rose is now run by IBM, so I don't know whether you can get much larger in software than IBM. That's just reiterating the models are good for facilitating discussion, but maybe the abstractions aren't necessarily the right things for implementation. The thing is, for most complex systems, the biggest problem is the requirements. The implementation is not generally the problem. The problem is getting the requirements right, and that's what the model-driven architecture is aimed at doing. And as it says, there's only certain cases where platform independence is really worthwhile. The one I think I told you in class, the one I worked on, the Rhapsody one, we deployed that system on a DVR, on a Fire panel, and I've forgotten the other one. There was another one. Oh, and an access control system. So that was pretty good. Okay, wrapping up. A model is an abstract view of the system. It lets us think about the system without developing it. The context model shows how it's going to be used. Use case and sequence diagrams describe the interaction between the system and its users. Structural models show how we're going to organize the system. Behavioral models describe the dynamic behavior. Activity diagrams can be used to model processing of data, and state diagrams to model the system's behavior.
And then finally, model-driven engineering is an approach to software development, which often helps for deploying the same system to multiple platforms. Can be very useful for that in that regard.
Okay. So again, as what our video mentioned, no, there are certain interaction models, no. All systems involve interaction of some kind. No, this can be either can be user interaction, which involves user inputs and outputs. No, interaction between the system being developed and other system, or interaction between the components of the system. The modeling, the modeling user interaction is important as it helps to identify user requirements. No, modeling system to system interaction highlights the communication problems that may arise. So modeling component interaction helps us understand if a proposed system structure is likely to deliver the required system performance and dependability. So he also discussed and give us an example about the use case modeling, as I mentioned, uh, the sequence diagrams, no, and the structural models. No? Structural models of software actually display the organization of a system in terms of the components that make up that system and the relationships. Structural models may be static models, no, which show the structure of the system design, no, or dynamic models, no, which show the organization of the system when it's executing. These are not the same things. No, the dynamic organizations of a system as a set of interacting threads may be very different from a static model of the system components. No, class diagram, on the other hand, are used when developing an object-oriented system model to show the classes in a system and the association between these classes. Loosely, no, an object class can be thought of as general definition of one kind of a system object. So an association is the link between classes that indicates that there is a relationship between these classes. Consequently, no, each class may have to have some knowledge of its associated class. No? Yes. The generalization is an everyday technique that we use to manage complexity. Rather than learn the detailed characteristic of every entity that we experience, we place these entities in more general classes, no, and learn the characteristic of these classes. This allow us to infer that different members of these classes have some common characteristics, no, and we can make general statements that apply all class members, no, because in modeling system, it is often useful to examine the classes in a system to see if there is a scope for generalization. This means that common informations will be maintained in one place only. And this is good design practice, as it means that if if changes are proposed, then you do not have to look at all classes in the same in the system to see if they are affected by the change. In object-oriented languages such as Java, no, generalization is implemented using the class inheritance mechanism built into the language. The aggregation, no, objects in the real world are often composed of different types. For let's say, for example, no, a study pack for a course may be composed of a book, no, PowerPoint slides, quizzes, and recommendations for further reading. Sometimes in a system model, you need to illustrate this because the UML provides a special type of association between classes called aggregation. That means that one object, or the whole actually, is composed of other objects, no, or yung parts niya. So the show is, we use a diamond shape next to the class that represent the whole, no. So another is the behavioral model. Now, behavioral models are models of the dynamic behavior
of the system as it executing. They shows what happens or what is supposed to happen when a system responds to a stimulus from its environment. And of course, the stimulus being two types like data and events. This will be aggregate association. Let's say 1:1, no, 1:10, and so on. Another, of course, is the data-driven modeling. No, data-driven models no show the sequence of action involved in processing input data and generating an associated output. They are particularly useful during the analysis of the requirements as they can be used to show end-to-end processing in the system. That is, they show the entire sequence of actions that take place from an input being processed no, to the corresponding output, which is the system response. When it comes to event-driven modeling, it shows how a system responds no, to external and internal events. It is based on the assumptions that a system has a finite number of states and that events may you cause transitions from one state to another. Let's say, for example, no, a system controlling in a valve may move from a state valve open to a state valve closed. So when an operator command or the stimulus itself is received, no, this view of system is particularly appropriate for real-time system. Event-based modeling was introduced in a real-time design method such as those proposed by Ward and Melior. No, the UML support event-based modeling using state diagrams, which were based on the state chart. No, state diagrams show systems, state and events that cause transitions from one state to another. They do not show the flow of data within the system, but may include additional information on the computations carried out in each state. Then, of course, the model-driven architecture. No, it is a model-focused approach to software design and implementation that uses a subset of UML models to describe a system. No? Executable UML, no? The fundamental notion of behind model-driven engineering is that completely an automated transformation of models to code should be possible. So to achieve this, you have to be able to construct graphical models no, whose semantics are well defined. You also need a way of adding information to graphical models about the ways in which the operations defined in the model are implemented. And this is possible using a subset of UML2 called executable UML or XUML. No? So, to sum up this discussion, no, in a system modeling, again, a model is an abstract view of a system that ignores some system details. Complementary system models can be developed to show the system context, no, interactions, structures, and behavior. Context models show how a system that is being modeled is positioned in an environment with other systems and processes. They help define the boundaries of the system to be developed. Use case diagrams and sequence diagrams are used to describe the interactions between user and systems, or user the systems being designed, and users other systems. Use cases describe interaction between a system and external actors, while sequence diagrams add more information to this by showing interaction between system objects. Structural models show the organization and architectural of a system, and class diagram are used to define the static structure of classes in a system and their association. Behavioral models are used to describe the dynamic behavior of an executing systems, and this can be modeled from the perspective of the data process by the system or by the events that stimulate response from a system. Activity diagrams may be used to model the processing of data, where each activity represents one process steps. State diagrams are used to model a system behavior in response to internal and external events. And lastly, model-driven engineering is an approach to software development in which a system is represented as a set of models that can be automatically transformed to executable code. Okay, so I think that's it for a system modeling.